In this video, we're going to take a look at section 1.5 on quadratic equations. Quadratic equations are equations of the form ax squared plus bx plus c equals 0. They're not always presented in that form, but if they can be rewritten in that form, then they are quadratic equations. The key characteristic of a quadratic equation is that the highest power of x is 2. So you have the ax squared. That's the key term that makes this equation quadratic. The bx doesn't have to be there. The c doesn't really have to be there. But the ax squared is key, and that you don't have a power of x higher than that is what makes this a quadratic equation. There are 3 different methods that we will learn to solve a quadratic equation, depending on what we're presented with. One method that we may use sometimes, it's kind of the more rare occurrence, is you can just solve for x. In other words, we're trying to solve all of these equations, but what I mean by you can just solve for x is you can just get x by itself and move everything to the other side. There are some cases where that will be possible with these quadratic equations, and that process will involve a square root at some point. So one method that we're going to learn is to use a square root and just get x by itself to solve a quadratic equation. We'll talk about when that method is possible. It's not always going to be possible. Another method that you hopefully are somewhat familiar with is you can use factoring to solve a quadratic equation. So if getting x by itself is not an option, the next option you would want to look at is, can I factor what I have here? And if I can factor it, that gives me a way of getting to the solutions. If, however, you can't get x by itself and you can't factor it, the last resort, the last option is to just use the quadratic formula, which we will talk about when we get to those problems. Okay. So use the square root property. So here the directions kind of give away. This one, you should be able to just get x by itself. At some point, you will apply a square root to find all the real or imaginary solutions to the following equations. I'm sorry it's grayed out for some reason. I don't know why it looks gray. I'll just rewrite it just to make sure it's visible to you. We have 3x squared plus 2 equals 0. So how do I want to say this? The giveaway, the red flag, the indicator that you can get x by itself using a square root at some point is if there's just one x in the whole equation. And one way that comes about is the middle term is just missing. So this doesn't quite fit the ax squared plus bx plus c equals 0 because the bx part is gone. It's still quadratic because it still has that first term, the 3x squared, that makes this a quadratic equation, but the bx term is missing. And again, that's okay. In fact, that's actually great because that means I can just solve this equation for x. If the bx term is not missing, that's when we have to use either factoring or the quadratic formula. All right. And so since there's just one x, okay, I'll try that again. Since there's just one x in the whole equation, we can just isolate that x. And it works in the usual way, right? So if I want to get x by itself, all the other stuff around it has to go. I'll start with the plus 2. I can cancel that out by subtracting 2 from both sides. So I get 3x squared equals negative 2 when I do that. And then the next thing that needs to go is the 3. It's being multiplied to the x squared, so I can cancel it out by dividing 3 on both sides. 3's cancel out here. And we get x squared equals negative 2/3. And the last thing that we are going to remove is this power of 2. How do we get rid of a power of 2? That's what square roots are for, right? A square root cancels out a power of 2. So if I want to cancel out this power of 2, I apply a square root to that. And so I end up with, initially, x equals the square root of negative 2/3. And so if that's as far as you take the problem, you might feel like that wasn't so bad, seems pretty straightforward, but this problem, I really like it because it seems friendly enough. It's pretty easy to just move everything to the other side. The square root part is maybe the most challenging part of this if you didn't know to use a square root there. But there's actually 3 things wrong with this answer. And so I like to quiz my class when we're having face-to-face classes, and I'll say, "What can you all help me format this answer correctly? Because this will not be correct when you type it into Math Excel." And there's 3 things that have to be corrected. And that kind of astonishes students because they're like, what could there possibly be? 3 different things? I don't see 3 things here. So I'm going to have to tell you, obviously, because, we can't interact. It's, asynchronous communication. But maybe you could pause the video and think about it for a second. What 3 things would you change on this answer to make it correct? One thing that you should identify, because we just talked about it in section P.7, is when you have a negative sign inside of a square root, that becomes the imaginary number outside the square root. Right? So that's one thing that we would need to do with this answer, is to rewrite it with an I. Right? The negative sign in the square root becomes I outside the square root. That's the imaginary number there. That's one change that we need to make. Another change that we need to make is this square root of a fraction is a problem. You really can't leave a fraction alone inside of a square root like this. What we need to do with that is apply the square root to the top and bottom of the fraction. So the square root applies to the 2 and separately applies to the 3. And the problem with this kind of expression is you do not want to leave square roots in the denominator. It's just improper formatting. It's not the standard way of writing a number, so it's just not written in a standard way. So we need to correct that. We want to get rid of the square root from the denominator, and sometimes students will think, well, okay, get rid of a square root by raising it to the second power, right? It's kind of what we used over here, but you can't do that with fractions. You're not allowed to square the top and the bottom because it just completely changes the value of the fraction, right? We want to change the way the fraction looks, but we don't want to change its value. And so we can't square the top and bottom to get rid of the square roots. What we can do is multiply the same thing to the top and bottom. And so what can I multiply to the square root of 3 that will get rid of the square root? Another square root of 3. And this always works with square roots. If you multiply a square root to itself, the square root will always go away. So what's going to happen here is we get square root of 3 times the square root of 3, which is going to be the square root of 9. Of course, the square root of 9 is just going to be 3. Right? And the square root's gone. And that's the way we need our answer to be formatted. If I multiply square root of 3 to the bottom, I got to do the same thing to the top to maintain its value. So we get square root of 2 times the square root of 3. Multiply those together, you get square root of 6. And so that's 2 things that we have now corrected. The last thing that we need to correct here is that I did not use a plus or minus on my answer. So anytime you are taking the square root of both sides of an equation, a plus or minus has to be introduced, because the result could either be positive or negative and still satisfy the equation. The reason that happens is, and I don't remember if we did this in a previous video for college algebra or if this is from a different class where I talked about this, so if I'm repeating myself, I apologize. But the square root of x squared actually does not just equal x like most people think, even though that's what we wrote over here. It actually equals the square root of x. Not the square root of x, what am I saying? It equals the absolute value. I said one thing and I'm writing the other thing, so I'm sorry, that was kind of embarrassing. It equals the absolute value of x is what I meant to say, and what it's weird. How did that happen? My brain was doing 2 things at once. It was saying one thing and writing something else, and I couldn't do that on purpose if I wanted to, but somehow it just happened now. So, and that's because if you think the square root of x squared just equals x, these are supposed to be equivalent to each other, which means they should always produce the same result on both sides. If I put positive numbers in for x, it works out fine. So if I put 2 here, we'll get square root of 2 squared equals 2, right? I'm plugging in 2 for x. 2 squared is 4. The square root of 4 is actually 2, and so it's perfect. It works the way it's supposed to. But if you use a negative number, so I was going to, instead of rewriting the whole thing, I'll just kind of insert it here. If I use -2 instead as my value for x, the right-hand side would be -2, but the left-hand side we get -2 squared, which again is going to be +4. And when I take the square root of +4, I get 2, and now it doesn't work for -2. So if I use negative numbers for x, they don't match each other. So square root of x squared doesn't just equal x. That's only true for positive values of x. It's not true for negative values of x. But we can fix that by just using an absolute value here. And that will take the absolute value of -2, make it a +2, and now they match again. And so the absolute value leaves the positive cases alone so that they still work, but it changes the negative cases so that they match up as well. And so now this statement is true for all values of x. The square root of x squared equals the absolute value of x. And so really, this is what we should have written. The absolute value of x equals square root of 2/3. But then we have to solve this absolute value equation, which if you recall from section 1.1, we actually talked about absolute value equations. You split this up. You get x equals the square root of 2/3, but you also get x equals negative square root of 2/3. Sorry, I kind of messed that up. Which is kind of a lot of mental processing, remembering that it's absolute value and then remembering how to process that absolute value. And so we kind of bypass all that and just use a plus or minus symbol. So I'm just explaining why. And I'm sorry if that irritates you, but I don't like to just say, you just put a plus or minus here and that's the end of the story. There's a reason for it. And so I want to explain to the best of my ability whenever I can why we do the things the way we do. And by having that background information, hopefully you'll do a better job of remembering to do this, because it's a common mistake to forget to apply that plus or minus, which is just going to get copied all the way down to our final answer. And so that was the third thing that needed to be addressed in that answer. And so the proper final answer for this particular problem is x equals plus or minus I square root of 6/3. All right, so it was a much more challenging problem than it might have first appeared. Here is another case, and again, the directions kind of give this away, that you can use a square root to solve this equation, which means you shouldn't have to factor, you shouldn't have to use the quadratic formula, you can just solve it for the variable. Just move everything else to the other side, get the variable by itself. At some point, you'll have to use a square root to make that happen. And when you look at the equation in this form, it doesn't even look like it might be quadratic, right? I mean, so we've identified quadratic equations as equations that look like this. The problem I'm currently given does not look that way, but I could make it look that way if I multiplied this out. So if I took z plus 8 and I squared it, which means you multiply it to itself twice, right? You don't distribute the exponent. You multiply it to itself twice, equals -36, and you FOIL here, you would get z squared. You're going to get some other stuff, but it would then look like a quadratic equation. So while it doesn't on the surface appear to be quadratic, if you worked with it, you could format it in that way. So it is indeed a quadratic equation. And this is actually a method that some students will use on this problem, which is not the quickest way or the easiest way to do this problem. So I'll have students on the test that take this expression, FOIL it out, and then get it equal to 0, and then try to factor it or use the quadratic formula. That's the hard way to do this problem. The easy way is to use the square root property and just solve for z, get z by itself. Now, for this particular problem, what will we do first to get z by itself? The first thing we will need to do here is the square root. So notice how that's different from what we did here. Right here, square root was the last thing that we did. But here it will be the first thing that we did. So depending on how the equation's set up, you might do the square root first, you might do it last, or you might do it somewhere in the middle. Usually it's going to be first or last, but sometimes there definitely could be a problem set up where you add or subtract first and then you do the square root, then you divide or multiply or whatever. And so they could mess with that order, but the standard problems are either you're doing the square root last or you're doing it first. In this case, we're going to have to do it first. So the first thing that needs to go is this power of 2. I can cancel it out by applying a square root to both sides. That square root cancels out that power of 2. What did we just learn about taking the square root of both sides of an equation? Well, again, if you were paying attention, you learned a lot that really this should involve an absolute value, and there's that whole story to it. But the shortcut is we just use a plus or minus, right? And you have to do it now. You don't wait till the end of the problem to find where to put a plus or minus. You apply the plus or minus after you take the square root of both sides. Whenever that occurs, a plus or minus has to be used. And so we will use it here. Plus or minus square root of negative 36. And then to get z by itself, we want to get rid of the plus 8. So now we will subtract 8 to the other side. And whenever there is a plus or minus involved, and then a number is being brought over by adding or subtracting, the conventional thing to do is to put it in front of the plus or minus. It just, again, I don't know if there's a human aesthetic to that makes that actually look nicer, or if it's just the way I was trained to think that it looks better that way. So but for whatever reason, it just doesn't look right for me if I put the minus 8 after the square root. It looks better to me when it's in front of the plus or minus. But I don't know how it looks to my students. And so technically you could also write it the other way. So I'm going to write it what I think of as the correct way first. But you could also have written it like this: plus or minus the square root of negative 36. Put the minus 8 after. Mathematically, they're the same, but this just looks better to me. All right. Then we want to simplify the square root. So remember, the negative sign means this will be imaginary. So we get I square root of 36. And this one, they're actually being kind of nice to us by giving us a number that works out nice with the square root. And so we have the square root of 36, which is just 6. And so putting all that together, we end up with the answer of z equals, don't forget the negative 8, let's just copy that down, plus or minus I times 6, which I would write as 6i. And that would be the final answer there. All right. This particular problem, we're told in the directions again, so read the directions. That they have been very helpful in guiding us on these problems. Solve the equation by factoring. Now this one, I'm almost tempted to say, forget the factoring, let's just use the quadratic formula. Even if it can be factored, this is one of the more difficult problems to factor because this is not a 1 here, it's a 16. So if you think about this formula, ax squared plus bx plus c, whenever a is equal to 1, that's the easy version of factoring. So if you have something like x squared minus 2x minus 8, there's a 1 here for a. This one's the easy case because all you have to do is find two numbers that multiply to negative 8 and add to negative 2. And once you figure out what those two numbers are, you just put them into your two factors and you're done. So it's a shortcut. So two numbers that multiply to negative 8, add to negative 2 would be negative 4 and positive 2. Right? They multiply to negative 8, they add to negative 2. And so I put negative 4 and positive 2 in the two factors with x, and it's factored. You can't do that here. If a is not equal to 1, you have to do it through the what I would call the normal process, or the full length process, which is the AC method or trial and error. And so I don't know what everybody's background is with factoring. I know that when I teach intermediate algebra, I teach to do these problems by the AC method. But that's more of a convenience for me as the teacher because it's just a nice step-by-step process. It's just easier to teach. Step 1, you do this. Step 2, you do this. And eventually you get to your answer. But trial and error is another effective way of factoring these kind of problems. But it's more of an art than a science. There's definite rules there that will help you figure out the answer more quickly. But it's trial and error. You're making guesses, and then you're checking to see if your guess is correct. And it can be kind of messy. And so I'm just going to do this one by AC method. But if you previously learned to factor these by trial and error, go ahead and keep doing it that way. I'm not trying to change the way you approach these problems. So a times c, a is 16, c is negative 3. So the AC method tells you to take a times c. That's going to be 16 times negative 3 in this case, which will be negative 48. And then you consider b, which is 2. And this part of the problem is actually pretty similar to what we did over here, we want to find two numbers that multiply to AC, but add to B. So two numbers that multiply to negative 48, let's try that again, negative 48, and add to positive 2, that's going to be positive 8 and negative 6. That multiplies to negative 48, that adds up to positive 2. And so we have these two numbers, but here's where there's a major difference. You do not get to just jump to the answer with those two numbers. It does not factor as x plus 8, x minus 6, even though it was similar to what we did over here. Because a is not equal to 1, we can't take that shortcut. We have to go the long way around, which is to take these two numbers and rewrite the middle term with those two numbers. So I'm going to rewrite 2x as 8x minus 6x. Right? It's the same thing, right? If you combine those together, you get back to 2x. I'm just writing it in a different way, and I'm writing it in such a way that the next step is going to be effective. It's going to work. Right? So this was step 3. Rewrite the middle term using those two numbers. We have 16x squared still, so we'll go ahead and copy that down. We have minus 3. We still have equals 0, but let's just kind of leave that out of the picture for the moment, and then we'll copy it down once we get done factoring. Then the fourth step is to use factor by grouping. So you'll group the first two terms together using parentheses. Group the second two terms together. Make sure that minus sign stays with the 6 inside of the second group. And by putting parentheses here without having something in between the parentheses, it looks like, oh, that's factored. You have parentheses and parentheses, right? Isn't that what factored looks like? Like over here, right? Parentheses next to parentheses is what we're trying to get to. And so this is misleading to write it like this. And a lot of students do, and I let it go if they still do the problem correctly, but it does kind of bother me a little bit. Really, there's still a plus sign here. Right? They're not being multiplied. They're not factored yet. All we did was throw some parentheses around a couple things. We didn't change anything about the problem yet. So the minus sign should stay with the 6. It should not stay in between the two parentheses. That would be an actual mistake that could prevent you from actually getting the correct answer. So make sure the minus sign stays with the 6x, and then you put a plus sign between the two parentheses to get started, right, at the beginning. Then you do factor by grouping. Well, that's what we're doing all together, I guess. Then you factor out the common factor, right? The common factor here would be 8x. What am I left with? I'll have a 2x left from the first term. And here I'm taking the whole 8x away, so it leaves a 1 behind. Here the common factor is 3, but if that's all I factored out, I would have negative 2x minus 1. What you really want here is for whatever's left over from this to match whatever's left over here. And so I want them to both be positive so that it'll match these two. So instead of just factoring out the 3, I'll factor out a negative 3. That'll change this to a positive 2x and change this to a positive 1. And now these two match each other, so now I can factor them out. So really what's happening here is you have two groups, which are really two terms, that have a common factor. The 2x plus 1 is a common factor in both terms, so you're factoring out the 2x plus 1 as a common factor now. So I put that out first. And then what's left over when you take that common factor away, you have an 8x left over from the first group, a minus 3 left over from the second group. Right, so that's how the AC method works. Again, I know I went through that quickly, but I think I mentioned in section 1.1 probably that factoring is something you're assumed to already know how to do in college algebra. It's technically, I'm not supposed to, I don't know if that's the right word to use, but it's not a topic that we're to take the time to teach. We don't have a lesson on factoring in college algebra. It's just, you're going to need to use it. We happen to need it here for this problem. Are we going to need it in the next section? No. Will we need it again in chapter 2? Yes. And so there'll just be various problems throughout the course where factoring is going to be required, and you're just expected to know how to factor. All right. But that being the case, I still like to at least review one or two problems as they come up to remind you this is how factoring works. Okay. Now that we have it factored, we're not even done, right? That was a ton of work right there, right? But remember, we're trying to solve an equation. Factoring is just part of that process. So the first step, and I guess I didn't even mention the steps here. I'm sorry about that. So step 1, actually a really important step that just really got overlooked here because it's already the case, is you have to set the equation equal to 0. That's really critical. It was already the case here that it was equal to 0, but if it wasn't, I would have to take the time to make sure it's equal to 0 first before I do any factoring, right? So I want to rewrite the 0 there. Okay. Step 2 is once you have it equal to 0, then you can factor, which is what we did, right? So step 1 was already done for us. It was already equal to 0. Step 2, factor. That's what we just spent all of our time doing on this problem, using the AC method to factor it. Step 3. Now, again, I like to give you a little background information about why this is going to work. But what we want to do in step 3 is set each factor equal to 0. So let me scroll down here. We'll set each factor equal to 0. So I take each of these factors and individually set them equal to 0. Sorry, I don't know what happened there with the plus sign, but I didn't want to leave it like that. It looked like an and, right? And then we take 8x minus 3 and also set that one equal to 0. Now, what allows that to be possible, the reason that makes sense to do, is this property of numbers. So again, this has nothing to do with algebra. It's just a property of numbers that we're using here to allow us to do this. And that property of numbers is this. So if I take two numbers, a and b, and I multiply them together, and I tell you the answer will be 0. And my zeros are looking really horrible today. If I tell you the answer will be 0, I don't know, I just can't seem to get those right. That's bugging me. Try one more time. What do you know about one of these two numbers? So if I tell you you're multiplying two numbers together, I'm calling one of them A, one of them B. Don't think of them as variables. They're numbers that I just don't want to be specific about. And I tell you that the answer is 0. What do you know about one of these two numbers? Well, one of these two numbers would have to be 0, right? Either A is going to have to equal 0, or B is going to have to equal 0 for this to be true, because the only way to get 0 as an answer when you're multiplying is for one of the numbers to be 0. So this is called the zero factor property, and that's exactly the situation we've set up here. So we had to do a lot of work, but we got to this point where we have two things being multiplied together, and we know the answer is supposed to be 0. Well, the only way two things can multiply together and be 0 is if the first thing's equal to 0 or the second thing's equal to 0, right? So this is like your A and your B. Right? Whoops, I hit the wrong button. So now I can't. So the one kind of annoying thing about this software is if I go back to the other page, because like the undo button and the previous page button, they look different, but they're both pointing to the left, you know, and the redo and the next page button are pointing to the right. And so sometimes I accidentally hit the previous page button when I mean to undo something. And when I go back to the page, because I went to a different page, it just locks everything in. So I can't undo what I did. So then I have to erase, and I'm sorry, I'm just complaining. But this is like A and this is like B here, right? So this is A times B equals 0. And even though these are variable expressions, they're still just numbers, right? Once you pick a number for X, this will be a number here, and this will be a number here. And so it's two numbers being multiplied together, and we know the answer is 0. So this logic comes into play. The only way for two numbers to multiply together and equal 0 is either for A to equal 0 or for B to equal 0. It's just in this case, instead of A, we have 2x plus 1, and instead of B, we have 8x minus 3. And so we set each factor equal to 0. So again, that's the background information. You won't have to go through that thought process every time you do one of these problems. This is all you have to think about, right? I set it equal to 0, I factor it, then I set each factor equal to 0. That's the thought process you want to go through. But there's a reason for it. There's a reason why we factored. There's a reason why we got it equal to 0, right? Every step has a purpose in math. So we don't do something just because it's fun to do or because we're trying to give you extra work to be difficult on purpose. The reason we have to set it equal to 0 is so that we can use the zero factor property. The reason we have to factor it is so that we can use the zero factor property. So those two things are the big setup, and then the payoff is that we get to set each factor equal to 0. And once we have each factor separately equal to 0, then it's just a simple case of getting x by itself. We just move everything else to the other side of the equation, and we get our solutions, right? So for this case, we subtract 1 from both sides, and then we divide by 2. And we get our first solution, which is negative 1/2. Right, so, if kind of tying it all back together, when x is negative 1/2, that makes 2x plus 1 equals 0. And when this is equal to 0, 0 times any other number is going to be 0. And so this will make the equation true. Let's find out when b is equal to 0. So we'll add 3 to both sides. We get 8x is equal to 3. Divide by 8 on both sides. And we get x is equal to 3/8. Okay, I'm not really happy. I almost hit the previous page button. Okay, I think that's the best I'm going to be able to do. So when x is equal to 3/8, that's when 8x minus 3 would equal 0. And when this is equal to 0, any number times 0 is still going to be 0. And so this would make the equation true also. And so there's 2 solutions, which I guess, I don't know if I did a good job pointing it out, but that's how many solutions we've been getting for every problem. The plus or minus, so maybe I should go back and talk about that. Like here, the plus or minus, it's perfectly conventional and proper and okay for you to write your answer with a plus or minus symbol. But I hope that you understand this means there are 2 answers here. There's negative 8 plus 6i, and there's negative 8 minus 6i, right? There's one answer where you use the plus sign, and there's another answer where you use the minus sign. And so if you wanted to write them separately, it would be like this. Math Excel used to require this, actually. Math Excel was pretty late in implementing the plus or minus button, and so you would have to type your answers in separately. But I don't know, I say fairly recently, but time goes by so fast the older you get, right? So maybe it was 5 years ago even, but they did eventually implement this plus or minus button. So you should be able to type your answers like this now. All right. And so we get 2 answers. Again, it's very common for quadratic equations to give you 2 answers. Okay, so let's take a look at this problem. So here, the first thing we're going to have to do is get it equal to 0. Now, unfortunately, we're not going to be able to solve this problem by factoring. And again, the direction's very clear about that. They're saying, to use the quadratic formula. And so that is the way we're going to have to solve this problem. Now, sometimes they will say use the quadratic formula when it could still be factored. And I'm perfectly fine if you just want to go ahead and solve it by factoring. I really advise students to apply the easiest method possible for solving the equation. And I think the order we've covered them in is the order you want to try to apply these methods. Try to solve it for x by using a square root first, if that's possible, because that'll be the easiest way to go. But if that's not possible, then try to solve it by factoring. And if that's not possible, then use the quadratic formula. So I really recommend going in that order. This one we won't be able to factor. So I can just look at the numbers and see factoring actually will not work out anyways. So we're going to have to use the quadratic formula. But the point I was trying to make originally is whether we're trying to solve it by factoring or the quadratic formula, the first thing you will need to do in either case is get the equation equal to 0. So the quadratic formula only works if it's equal to 0 as well. And so the first thing we need to do with this is to subtract the 10x back to the left-hand side. And so, let's see, I'm not really happy with how that x came out. All right, and so we'll have x squared minus 10x plus 41 equals 0. And I'll put the minus 10x in the proper spot, right? You want the x squared term first, then x, then the constant, and that's the way I have it written on the screen. Then we should, again, and I've already given the game away, but the next thing I would try to do with this is, well, I can't solve it for x because there's x in 2 different places. So remember, solving it for x using a square root only works if there's only one x in the whole equation. Now, there is actually a process for taking one of these that has 2 x's and rewriting it so it only has 1 x, and it's called completing the square. And in fact, we talked about completing the square in section 1.3 with circles. So you actually can use that method here to rewrite these 2 x's with just 1 x. But I'm not going to teach the problems that way. Most students don't really prefer that method anyways. So usually students are pretty happy just using the quadratic formula. So anyways, got a little sidetracked. So I can't solve this for x the way it's given to me unless I want to do the completing the square thing. And So that method's not possible, right? You can only use that method of using the square root if there's just one x in the equation. The next method, factoring, that's something to look into, right? In fact, it is kind of nice here because a is equal to 1. So if it can be factored, I just need to find two numbers that multiply to 41 and add to -10. But 41, I believe, is a prime number. You can't even break it down in any different way. So there's just no way to find two numbers that will multiply to 41, but then add up to -10. And if you can't find two numbers that fit your description that you're looking for, whether you're doing AC method or the shortcut method that we're using here, it can't be factored. And if it can't be factored, you have to use the quadratic formula. Now, the quadratic formula is derived by taking this formula here, ax squared plus bx plus c equals 0, and doing the completing the square process that I just talked about. So the first thing you have to do is factor out, well, first thing that you would do is subtract the c to the other side. So you get ax squared plus bx equals -c. Then you can't complete the square when a is here. So you actually have to factor it out. Even if it's not a common factor, you have to factor out the a. And the reason this becomes kind of a problem is because then you end up with a fraction here. So it looks like this. Right. I guess I'm trying to remember. I haven't done this in a while, actually. So it kind of looks like this. And then you find, you take the b term here, which is b over a, divide it by 2, and then square it, right? Just like we talked about in 1.3, it's the same process. And that tells you the magic missing number that you need in order for this to factor as a perfect square. So the thing I kind of was hesitating on is, what do I do with the a? I'm pretty sure you just want to divide that to the other side. So anyways, I'm not going to go through all the details of that, but if you were to continue on this process, you would eventually get something that looks like this. You would end up getting x plus b over 2a, right? And you can kind of see that happening here, right? Because dividing by 2 is the same as multiplying by 1/2. So you get b over 2a here. Squared equals, over here you would have, I'm trying to remember now, I might have to do the same thing over here and combine like terms. I'm pretty sure, okay, yeah, that's what you're going to get. You get b squared minus 4ac over 4a squared. I'm pretty sure is what you get there. All right, and then you take the square root of both sides. And again, I'm going to skip a couple more details. And if you're interested in the details of this, I'm sure there's plenty of YouTube videos or websites that will fill these details in for you. But you eventually get -b plus or minus the square root of b squared minus 4ac, the whole thing over 2a. Right? You can see 2a showing up here because when you take the square root of this, square root of 4 is going to be 2, square root of a squared is going to be a, which again technically is absolute value of a, and that's actually something you have to address in a proper proof for this formula, but we're just going to let it go at that. And so this is the quadratic formula that you would need to memorize. So essentially what the quadratic formula is doing is it's completing the square for you. So it takes the equation, completes the square for you, solves it for x for you. It just does all this work behind the scenes and just spits out the answer, which probably sounds too good to be true, because it is. Because even though it does solve it for x, it does all this work for you, the answer it spits out is just a mess. And so you have to take some time to whittle it down, simplify it. And that's where all the work comes in for these problems. Is getting the answer is easy. You just dump the numbers into that formula. But then simplifying the answer is where all the work is at. All right, so here a is 1, as we already mentioned. B is -10. C is 41. We're going to plug those numbers into this formula that we just wrote on the screen. I'll write it again. And that is really my recommendation, is to write it every time you're going to use it, because it'll help you remember it. Now, with, I don't know if I'm going to change policy on this, but generally I require my students to memorize this formula. So that's why I was kind of saying, write it down every time you use it so you can remember it. So on the test, you'll know it, because I usually don't give this formula on the test. But I don't know, with circumstances changing, maybe it's just better if I just include a formula sheet. I don't know. Check with me if you're in my class, or I'll probably make it clear to you, depending on the situation, whether we're face-to-face or still doing remote learning because of the COVID-19 stuff. We'll have to determine like the best way of, administering the test. And under those circumstances, I'll have to decide what's the best thing to do with formulas. Because like if students are testing at home, they're probably going to use the formulas anyways, even if I don't provide them on the test and tell them that they even if I say don't use the formulas, you have to memorize them. I don't know if I can prevent that if it's like remote testing. So anyways, I'll let you know if you need to know this formula or not. Semester to semester. I'll just kind of make that decision as needed. All right, so we'll have x equals, we have a negative sign in the formula, negative, and then b, which is negative 10. So that's a common pitfall. When b is negative, be careful, you get a double negative there. Plus or minus b, which is negative 10, squared. Another common pitfall. Minus 4 times a, which is 1, times c, which is 41. The whole thing divided by 2 times a, which is 1. We just solved the equation, just like that, right? It's really quite amazing what the quadratic formula does, right? It just did all of this work for us, solved it for x, and produced the answer. Just all we had to do is plug in a, b, and c. But we can't leave our answer looking like this. It's a mess, right? So we have to simplify it. As I mentioned, double negative here, so this is going to come out positive 10. This is going to be negative 10 squared. Now, the mistake students make here is when you square negative 10, it comes out positive 100. I will often have students put negative 100 there, so be careful about that. Squaring a number always comes out positive. So this b squared term should always be positive, right? Unless there's an imaginary number there, but I'm not going to give you a problem where that would happen, right? Minus 4 times 1 times 41 is going to be 164. Over 2 times 1, which is going to be 2. So it doesn't take too long to really get this in a respectable looking form. We get positive 10 plus or minus. This will be the square root of 100 minus 164. That's going to be negative 64 over 2. All right, so it already looks a lot better than it did originally. But we can do more, right? Negative sign here, remember, we've seen this multiple times today, or in this video, is imaginary. And then the square root of 64 is just going to be 8. So putting that together without having to do too much more writing, we get 10 plus or minus 8i over 2. And then we reduce, right? And we can divide the 2 into each term separately. So we get 10 over 2 plus or minus 8i over 2, which reduces to 5 plus or minus 4i. So we actually get a pretty nice answer, which in a way is kind of bad. Getting 64 here, you might have been happy to see that because you're like, oh, 64, I can take the square root of 64. I know what that is. It's going to be 8. But because you can simplify it, it just means there's more work. Now, if I got something here like 131 or something like that, that'd be better, really, because you can't simplify square root of 131. You'd be done already. And so it's one of those cases where it's nice to get nice results that we can feel more confident about, but it does mean more work in getting it simplified as far as we possibly can. All right, so that is the answer there. All right, so this is another one. Use the quadratic formula to solve the equation. So why don't we save a little bit of time in this video? You pause the video, use the quadratic formula to solve this equation. I'll pause the recording and do the same, and then we'll both resume, and then you can check to see if you came up with the right result. Okay, so here is the result that you should have come up with. X equals negative 1 plus or minus I square root of 39 over 4. So this was kind of what I was talking about in the last problem, the last example. Getting a number that actually is unpleasant in the square root, because if it can't be simplified, then you're just done. So notice this was actually less steps than what we had to do in the previous problem. It was already equal to 0 for one thing. Then here we get 1 minus 40, which is negative 39. Now the negative we still need to write as the imaginary number, but then square root of 39 doesn't budge. There's just nothing we can do with that. So that's our answer. That's the best we can do. And there's nothing to reduce or anything like that. So you can just leave your answer in that form. And so that's the answer you should have come up with. All right. You can also solve quadratic equations by graphing, but to do this, especially with some of the problems that you might come across, you would need to use technology. So having like a graphing calculator is the ideal way to use graphing to solve these. And this method only works if the solutions are real numbers. So we could not solve this problem by graphing because the solutions are imaginary, so they would not show up in the graph. Right? But here, they've kind of done all the work for us. They've given us an equation, negative 0.5, which is just 1/2, x squared plus 1.5x plus 20 equals 0. So it's a quadratic equation. In order to solve this by graphing, what you do is you graph this as y equals whatever that expression is. So we're graphing y equals negative 0.5x squared plus 1.5x plus 20. So that's the graph that you see, and they already did the graph for you using technology. So where do you suppose on this graph we would find the solutions to this equation? Well, we're looking for where it's equal to 0, but we set this equation equal to y, right? So the equation is simultaneously equal to y for the graph and also equal to 0 for our problem. And so we put those together and we find the solution where y is equal to 0. So the way you can solve these quadratic equations by graphing is to set them equal to y, so you can graph them on the Cartesian coordinate system, and then looking on the graph for where the y coordinates are 0, which will be the x-intercepts, right here and right here. So here, y is equal to 0, and here, y is equal to 0. So these would be my two solutions, and you want the x-coordinates of those points. So x equals negative 5 is one solution, x equals 8 is the other solution. And so that's where you would get them on a graph. So that's where you would get the solutions on a graph. So putting that all together, you can solve these quadratic equations by graphing, by setting it equal to y, and finding the x-intercepts on the graph. That'll be the solutions to your equation. So for this particular problem, how many more do I have? I have 2 more, and I have a word problem that I want to do. So I don't think I'm going to completely work this problem out. But what I wanted to talk about was just the setup of it. Because once you get it set up correctly, it's just like the problems we've already done. And I don't want to get too repetitive in the video. But this problem starts off looking quite a bit different than the problems we saw previously. Really, this is not a quadratic equation, not yet. It's not the right form, right? We need it to look like this in order to consider it to be quadratic, or something that could easily be made to look that way. And this doesn't look like that, right? It has fractions where, not just fractions, but the variables are stuck in the denominator. So this is really a rational equation, which is something that we saw back in section 1.1. And the way we dealt with rational equations is actually what we need to do here. It's going to be a little easier this time, though, is to get rid of the fractions by multiplying the common denominator to both sides. So what is the common denominator here? Well, both denominators have a variable p, but this one's to the first power, this one's to the second power. So if you thought that the common denominator would just be p, that's almost right, except it doesn't quite get the job done. So if I multiply the right-hand side by p, it doesn't cancel out both powers here. It would only cancel out one of them, and this would still be a fraction. It would still have a variable in the denominator, and I still would not be able to solve it. So the common denominator, and I think I mentioned this in 1.1, even though it never came up in that section, is that whenever you're putting your common denominator together, you raise each factor to the highest power that occurs. So what are my factors here? Well, p is the only factor. What's the highest power of p that occurs here? It's 2. And that's what you want to use in your common denominator. So we multiply both sides by p squared. You have to distribute it, and it multiplies to every term, whether it's a fraction or not. So this is going to actually become 7p squared plus 8p equals 12. Right. So what's happening here to get 8p is one variable p cancels out. Right. We have p squared here, but one of those will cancel out with this p in the denominator, and so I'll have one left. So that's how we get 8p. On the right-hand side, the p squares just cancel each other out, and that's how we get 12. Now it's just an ordinary looking quadratic equation. You do need to get it equal to 0 first before you do anything else. And these numbers are not looking very friendly, but you could try to factor it. It may be factorable. I feel like we've already come this far. Maybe we should try to finish the problem out. I don't know. I don't want to take too much time, but I kind of feel like this might be factorable. But and that's the thing about factoring. If you're not sure how to factor it, if it looks menacing and difficult to factor, then just use the quadratic formula. It's fine. Even if you could factor it, maybe it's just easier, instead of trying to figure out how it factors, to just use the quadratic formula instead. So for a problem like this, I'm really kind of 50-50 on it. Yeah, maybe it could factor, but what if I'm wrong? I spent all this time trying to see if it could factor, and what if it doesn't work out? I got to use the quadratic formula anyways, right? So maybe quadratic formula is just the better way to go when the factoring gets to be this difficult. So it's going to be 7 times negative 12, which I do know is negative 84. I happen to know that one off the top of my head. What I'm not sure about, and I still haven't thought of it yet, is are there two numbers that will multiply to negative 84 but add to positive 8? So I'm trying to think. 28 and 3 doesn't work. Oh yes, 14. Now, the reason, here's a little trick that I use for bigger numbers here. And this isn't even the worst of it. I mean, sometimes you can get hundreds or thousands here for a times c, is to go back before the number gets this big. So go back to the 7 times the 12 and try to split these numbers up in a different way. So my first thought was 4 times 3. I could rewrite 12 as 4 times 3. And then what you can do is regroup, right? Now 7 doesn't really split up in any other way, so you're just going to have to keep that as a 7. But then I could regroup these. So I could take 7 and 4 together, which gives me 28 times 3, right? That would also be 84, but that obviously doesn't add up to 8. And then I thought, well, you could, instead of grouping the 4 and the 7, you could do the 3 and the 7. That gives you 21 and 4, but again, doesn't even get you close to 8. So I'm like, okay, that obviously is a dead end. What's another way you could write 12? You could write it as 6 times 2. And so you can take the 2 and the 7, so we gave up on that, which gives you 14, and that leaves you with 6, and what do you know, the difference there is 8. And so those are your two numbers, 14 and 6, which I would never have thought of if I'm thinking of the number 84. I would never think, oh, 84, obviously 14 times 6. Those numbers do not come to mind for me when I think of the number 84. So I would not have thought of it otherwise. So that's just another trick I use. The other thing you could do is just make a list. 1 times 84, 2 times 42. Eventually you would get to 6 times 14 if you were thorough, right? So this is going to be positive 14 and negative 6. So you can split this up, write this as positive 14p minus 6p. And then you do the factor by grouping thing. And I think I'll just go ahead and stop there. I don't know, why not? Okay, how about I do this? I'll pause the video because I just feel bad. Like, I don't want to be repetitive. We kind of did a problem like this already. I'll just pause it. And then you can just see what the answer is without having to... Okay, I kind of had to laugh at myself there because I really just cut I was talking too much for my own liking. I was talking, but then my mind cut me off. So I hit the pause recording button before I finished talking there. So I apologize for that. But there's the solutions you should come up with. P equals negative 2 and P equals positive 6 over 7 when you finish factoring it and solving it for P. All right, let's look at this last problem. It's a word problem. The demand equation for a certain product is P equals 30 minus 0.005x, where x is the number of units sold per week, and P is the price in dollars at which each one is sold. So in economics, you would learn a fundamental property is that the number of units you sell of a given product is related to the price of that product, right? And it's kind of this, and it affects the supply and demand, right? So if you lower the price of something, you will sell more of it. If you raise the price of something, you will sell less of it, because at a higher price, there's going to be less demand. At a lower price, there'll be more demand, right? And so for this particular company, they actually were able to mathematically model how their price relates to the number of units that they're going to sell. And they came up with this equation that the price equals 30 minus 0.005x, where x is the number of units that will be sold. All right, the weekly revenue is given by R equals X times P. All right, so they're kind of giving us this information in bits and pieces, and we're going to have to put it together to get a quadratic equation out of it, right? But this revenue, revenue is just how much money are you bringing in. It's not profit. It's just how much money are you bringing in. And for this particular product, it'll be however many of that product we sell, which we already said was X, right? X is how many are you selling times the price of each one that you sold. And that tells you how much money you've earned, right? And so it's a very simple formula. It's the price times the quantity. That's the revenue. All right. So But the price is also determined by the number of units that we're going to sell. And so we can plug that into this formula. So x will just stay x, but the price is 30 minus 0.005x. And we need to use parentheses there because that has to get multiplied by x, right? What number of units sold produces a weekly revenue of 28,800? So this is the revenue that we're being given. And so we're going to have to plug that into the formula as well. So 28,800, I left out the 8, right, is the revenue they've given us. And so we plug that into the formula also. So like I said, it's all there, but we have to take all that information and know to plug it into this formula here to get our equation. And it may still not look quadratic, but it will once we take the first step here, which is distribute the x into the parentheses. So we get 28,800 equals 30x minus 0.005 x squared. So this is a quadratic equation. The first step, whether we're going to solve it by factoring or the quadratic formula, is to get it equal to 0. Now, it probably would appear that the quickest way to get it equal to 0 would be to subtract the 28,800 to the right-hand side, which would be the quickest way, but I have a reservation about that. And that reservation is I don't like when a is negative. I find it's more difficult to factor. The quadratic formula acts a little more wonky when a is a negative number, to me. And I feel like I'm more likely to make a mistake or just have more difficulty with the problem. So I really, really prefer myself and would advise my students to always arrange it so that a is a positive number. So even though it might seem like a little more work here, I'm actually going to move these two things back to the left-hand side just for the sake of making this value positive, because I'm going to have to add 0.005 x squared, and then I'll have to subtract the 30x, but that makes sure that a is positive, 0.005 x squared minus 30x, and we're going to put that in order from highest to lowest power, so we'll have positive 0.005 x squared minus 30x plus, because it's a positive number here, so we'll have to put a plus sign in front of it, 28,800 equals 0. Now, I believe this will be factorable, and I know that because I think and not that I guess models have to always produce perfect results. It could be that this equation might give us x equals 3.5, but you can't sell half a unit, right? So if we got an answer like 3.5, we'd have to round that up or down to a whole number because you can only sell whole numbers of units. But I think they've chosen these numbers carefully enough that we will get nice answers. And if you're going to get nice answers, it means it can be factored, right? You don't get, how do I want to say this? Like, if the answers work out nice, then the equation is factorable. But how would I have to factor this? Look at these crazy numbers, right? A times C would be 0.005 times 28,800, whatever that might happen to be, which maybe it should shrink the number down, but still, it just seems like a tough way to go. So even though I'm sure this could be factored, because of the numbers I'm dealing with, I'm just going to use the quadratic formula, right? I think it'll just be easier that way. So we'll take negative b plus or minus the square root of b squared minus 4ac over 2a, right? I'm trying to do what I say, which is write it down every time you got to use it. It'll help you remember it. So b is negative 30. So we're going to have negative of negative 30 plus or minus the square root of negative 30 squared minus 4 times a, which is the 0.005, times c, which is the 28,800. Hopefully I have enough room here. I'm going to skip writing the comma. Over the whole thing, over 2 times a, which is 0.005. Now, I'm going to simplify this, right? Because there's my solutions. I can't see my cursor. Okay, it looks like it finally unfroze. All right. I'm kind of worried because like I can see my webcam image and it looked like it was frozen. It's working now though, but I apologize for that little glitch. All right, so let's go ahead and simplify this like we did before. This is going to be positive 30. I'm not going to put plus or minus there. Now I happen to know 3 squared is 9, so by throwing that 0 on there, this is just going to be 900. Minus, now this one I feel like I'm not going to be able to figure out. off the top of my head. Let me grab my phone real quick. It's about to die earlier, but it's 50% now, so I should be good. And we're going to have 4 times 0.005 times 28,800. It's going to be 576. All right. And then 2 times 0.005. I probably should be able to do that in my head, but I'm not going to try. It's been a long video. My brain's starting to tune out a little bit. So, all right, it's 0.01. So what we end up with is 30 plus or minus the square root. Again, I should be able to do this in my head, but 900 minus 576, 324 over 0.01, which is going to give me 30 plus or minus. Now, if my intuition was correct and this would have been factorable because we're going to get nice answers, this square root should work out nice. And I feel like I know this one. Like square root of 400 is 20. Is it 16? No, 16 would be like 256. No, 16. Yeah, 256. I think this is 18. All right, so square root of 324. I'm pretty sure about this. I don't think I need to check it. It's going to be 18 over 0.01. Now, with the other problems, you could do this here, but I kind of feel like it doesn't make sense. But you could divide the 0.01 into each of these separately, and you'll get bigger numbers there. But in the previous problems, because the square root didn't work out perfectly, or because it was imaginary, we could leave our answer in plus or minus form. But not so if the square root works out nice. So if you had one that was factorable and you get a nice answer from the square root, you cannot leave this answer in plus or minus form. You have to consider both answers separately and then simplify further, because what should end up happening here is we can get a single numerical answer for both, right? For the plus sign and for the minus sign. So rather than leaving it as this kind of complicated plus or minus expression, we should separate them and just whittle them down to single numerical values, right? So we'll get 30 plus 18 over 0.01 and 30 minus 18 over 0.01. And so 30 plus 18 is going to be 48 over 0.01. And I just happen to kind of know a shortcut for dealing with this. Dividing by 0.01 or 0.001, all that does is move the decimal place of the number on top. So this will actually move it twice to the right. So there's 2 decimal places here. It'll get moved twice to the right up here, and you'll get 4,800. This one we subtract, we get 12 divided by 0.01, and so we get 1,200. So there's 2 answers. There's 2 reasonable answers. You might say, wait a minute, how can, for this word problem, there can't be 2 answers that are right? But in fact, there is. They're both correct. And so you might wonder, how can they make the same amount of money selling 4,800 units as they would selling 1,200 units? And the way they make the same amount of money either way is the price will be different. If they want to sell 4,800 units, it's going to have to be at a lower price to sell that many. If they only sell 1,200 units, it's because they had a higher price on it, so they sold less. But because the price was higher, they made the same amount of money that they would for 4,800 at a lower price. So as a company, you kind of want to find the sweet spot of how can we sell the most units. Maybe not the most units, but again, if I was working for this company and I thought I can make the same amount of money selling 4,800 as 1,200, I'm going to just do 1,200 because it's the same amount of money and I get to hold on to more product and I'll be able to sell more 1,200 units, right? Instead of, because how much is 1,200? That's like 4 times, right? I mean, I could sell 1,200 units 4 times and match that 4,800 number of units, but make $28,800 each of those 4 times, right? So you analyze the price and the quantity and the relationship with that to try to maximize your profits. And so we're going to talk more about that in a later section about how we could, try to find the maximum revenue or the maximum profit based on these kind of equations to get the most money possible. But that'll be for a later time. So anyway, sorry I kind of rambled there at the end. Thank you for watching this video on section 1.5, quadratic equations. I'll see you in the next video, section 1.6.